Welcome back to our second talk of the morning. So it's a great pleasure to have Pengzi Miao talking to us about mass capacitary functions and the mass to capacity ratio.
Thank you. Thank you for the introduction. And first, I want to thank the organizer for organizing this event. And I also want to take the chance to say that thank you for making our participation online available. In particular, when I see Dr. Yu Guangxi's talk earlier, I realized that I haven't been to his office for over 3 years. So being able to see Dr. Xi virtually and his office is something that's very special to me. So I just want to thank the Institute and thanks the organizer for making this happen. All right, in this talk, I'd like to discuss something regarding mass and capacity. Let me begin by giving you a talk outline. So basically, this talk is organized into 5 parts. In the first part, I will talk about the relevant definitions and previous results. And then I'll talk about detecting the mass at infinity. And I will move on to talk about 2 groups of geometric inequalities. And in the end, I will discuss about certain class of manifolds with this special mass to capacity ratio band. And let me say, make a remark that this past June, I gave a talk at the Simon Center. At that stage, my talk is really about this part that I circled. So, so today, I truly hope I will get to the second part as well. So that's an outline. Okay, the definition of an asymptotically flat. Asymptotic flat manifold. As you see in this talk, I will be only talking about dimension 3. And we can ask, what can one say in higher dimensions? But in this talk, I will be only talking about asymptotically flat 3 manifold. So this is the definition. A manifold is asymptotic flat if outside a compact chart. The metric behaves like the Euclidean metric in this precise sense. And we do assume the scalar curvature is integrable. And under that assumption, one has this well-defined ADN mass. It was proved by Barnick and Crucial independently that this mass is a geometric invariant, independent on the choice of the coordinate. Okay, next, let's review the concept of the capacity. So here, I'll draw a picture. So consider a asymptotic flat manifold with boundary. Say the boundary we denote by sigma. The capacity of this manifold is nothing special. It's the infimum of this Dirichlet energy of all the overall Lipschitz functions f, where f equals 1 at the boundary and f decays to 0 at infinity. And then we know this infimum is realized by a harmonic function, which is 1 on the boundary and goes to 0 at infinity. Now, in the case that we are in R3 in the Euclidean space, this has a very vivid physical contact. So given a conductor sigma, the boundary of a solid, then the capacity is nothing but the amount of the electric charge when spread on the surface to raise the electric potential on the surface to be 1. The electric potential is 0 at infinity. You raise the electric potential to rise to be 1. How much amount of charge you spread on the surface? So that's this capacity. And in the rest of this talk, I will be working with 1 minus phi. for the only reason that if I work with u equals 1 minus phi, then heuristically the gradient of u points towards infinity, and that's the direction with respect to which the mean curvature of a surface is defined in my convention. So, so if you consider harmonic function, which is 0 on the boundary, which is 1 at infinity, then you know on the boundary, the gradient vector points towards infinity. All right, so that's the concept. Any question? Okay, if not, so regarding the mass, one has the fundamental theorem of remaining positive mass theorem, first proved by Miao using minimum surface, and then soon by Witten using spinors. So the theorem says, if MG is asymptotically flat, complete, three-manifold, three-dimension with non-negative scalar curvature without boundary, say, then the mass is non-negative. And it's 0 if and only if the space is the Euclidean space. So that's a positive mass theorem. Now, regarding the mass and capacity, regarding a relation about mass and capacity, Bray obtained the following mass capacity inequality in the case that the boundary is the minimum surface. So, here I draw a picture where the boundary has two connected components. So as long as the boundary is minimum, it has mean curvature 0, Bray shows the mass is greater than or equal to the capacity, and with a rigidity property. And this proves Bray's argument uses PMT. And therefore, you see there is no topological assumption. It works for multiple connected boundary components. And this is a key step in Bray's proof of the general three-dimensional remaining Penrose inequality. Okay, so that's, okay, this is the result on mass and capacity when the boundary is a minimum surface. And then using the method of the weak inverse mean curvature flow developed by Huskin and Emanen, Bray and I consider the following question. So what if the boundary of an asymptotic flat three manifold may not be a minimum surface? And what can one get? Well, what can one say between the mass and the capacity? And this is the result we had back in 2008. And it's obtained under two assumptions. One assumption is on the boundary mean curvature. And basically this assumption says the Hawking mass of the boundary is non-negative. So in that sense, it's a quite reasonable physical assumption. And then there is a topological assumption. This topological assumption arises due to the method we use. Because we are using inverse mean curvature flow, so we assume the boundary is connected to start with. And we also want some assumption that would guarantee the leaf of the flow has this Euler characteristic bound. Say a sufficient condition is to ensure if it remains connected. And this H2M relative to the boundary condition is a sufficient condition under which one can prove the weak inverse mean curvature flow remains connected. So this condition is also quite, I do not know how to remove this condition when using this inverse mean curvature flow method. So under these two conditions, this result gives a bound of mass over the capacity by something local.
Sorry,
right?
can you
Yes.
I think you said what the interpretation of the bound on integral h squared was, but I missed it. Can you repeat it, please?
Right. This really says the Hawking mass of the boundary is non-negative.
Thank you.
You're welcome. And as I remarked, that assumption is quite physical. I mean, physically it's quite natural. But later in this talk, we will see that as a byproduct of this work, I'm going to, sorry for that. Okay, I'm going to talk. Okay, this assumption can be removed. So later on, I will remove this assumption. Okay, so now let's move to, okay, let's proceed. So here is a very brief account of the current known proof of the three-dimensional positive mass theorem. So since the original work of Shen, Yao, and Witten, other proofs of PMT in three dimensions have been given. It's given by Husken and Imanen in 2002 using inverse mean curvature flow. And then in 2018, it was proved by Yu Li using Ricci flow. And then in 2019, Bray, Catherworth, Curry, Stern, they proved the PMT using harmonic functions, which are asymptotic to a coordinate function. And last year, Angostiani, Mazuri, or Renfield, they proved the positive mass theorem using green function. And later, I will show you as a byproduct of this work, and we will give a few extra arguments showing PMT. So this is the first part of this talk. Now we will move on. Regarding the mass, there are various ways to detect mass besides the original definition, the ADM definition. There are other ways to compute the mass. In this work, this is what we found. Let's consider an asymptotic flat three manifold. And for this result, I do need this additional assumption of the decay of the metric. So the usual definition of asymptotic flatness requires the metric decay up to second order. Here, for technical reason, I will mention in a second, I need the metric to decay up to third order. Okay, under this assumption, now near infinity, you consider a harmonic function which goes to 1 at infinity and has the following expansion. So basically, this says the harmonic function is strictly less than 1 near infinity. And then one can consider the level set at infinity. For this result, it's really a result, a local result near infinity. It's something about the mass. So it's a local result of a asymptotic flat manifold near infinity. So if you take t close to 1, every level set is a regular surface. And then there are two ways to compute, to detect, or to see the mass. The first one says this limit. So a pi subtract 1 over 1 minus t times the integral of the mean curvature with this weight by the length of the gradient of u. Before you do this division, you can easily compute that this quantity goes to 0, and therefore what this limit suggests is, in a sense, the derivative of the quantity of this difference at infinity is represented by this mass to capacity to C ratio. Okay, at this stage, you do not need to introduce the concept of capacity yet because it's just a local result. So it's a mass to C ratio where C is this coefficient. And the second one even does not involve the C1 data of the metric. The second formula only involves the length square of the gradient of u integrated on the level set after certain scaling and difference, and then taking limit. Okay, a technical part in the proof uses a previous result of Yu Guang, of Xi, and Guofang Wang and Jie Wu back in 2009. And there they showed the Hawking mass of a family of nearly round surfaces tends to the ADN mass. And to check that the level set of this harmonic function U is nearly round, I need to put that assumption, the assumption that U decays up to third order derivative. All right, so this is about how the mass comes in terms of this function where, by the way, I think I use the word capacitary function. So let me make a comment that for this function, for this function U or phi, I mean that's the capacitary function. I meant. Okay, so I should mention that earlier. Sorry. Okay, one remark about these math formulas. One thing I want to say, there are indeed motivations behind this formula or these two formulas. These are not a result of some mysterious calculation or some luck. There are indeed a motivation. I don't want to say, I don't have time to say a lot for the motivation, but let me just briefly say, let's look at this formula one. So basically, one can compute this integral of h with the gradient length u weighted on different surfaces, on different level sets. And if you do that, you will have a Willmore functional term, integral of h squared shows up. And then naturally you want to relate that by the Hawking mass. And then you relate Hawking mass to the mass. So if one follows that direction, one will be led to such a mass formula. Okay, that's remark one. Remark two. Okay, now
Wait,
you
can
can
I ask a quick question
yes.
about remark one?
Sure.
Is that you
Sure,
said on
please.
level sets?
On level set, yes. Yes,
Of the
so,
inverse spin curvature flow?
No, here, it's about a harmonic function. So U is a
Level sets
harmonic
of U.
function. Level set of U.
Okay.
Yes.
Thank you.
Yes. No problem.
Sorry, and in that intuition, so of course you get an integral h squared over the level set term, but you also get an integral grad u squared. So do you also relate that to the capacity or no?
That term, well, it's more than that. It's more than just using holder or Cauchy holder. So that term is, I mean, okay, I have that expression written. But that term, the gradient of u square. So indeed, if you take derivative, if you okay, let me color, the derivative of the second one is related to the first one, or the other way around. Yes, you do need to do some work to deal with that. It's not. I mean, the gradient of u square integral is appearing in the second part. So the way that I found this formula is I first get the first one, and then by doing a derivative calculation of the second one, then the second formula follows from the first one.
Right. And so is the C here related to the capacity, or it's not at all?
Yes, that's a very good question. That's my next comment. Yeah. Okay, so the previous result, the mass formula is local at infinity. In application, one can apply to such a scenario. If you have a symptotic flat manifold with boundary, then you consider such a harmonic function u equals 0, u goes to 1 at infinity. And in this case, if you are considering this u, then this coefficient c is a capacitor. And that's I think that's the answer to your question. In general, for the math formula, no, you do not need to assume this. I mean, it's a local result. It's something it's a statement at infinity. As long as you choose Laplace u equals 0, u goes to 1 at infinity, and u has a symptotic expansion, and then mass over c is computed by that formula.
I guess even in that case, though, I guess the C is still the capacity of this level set close to infinity.
Yes, of its level set after a certain
That's right.
scale. Yes. All right. So that's a remark about the capacity and C. Now here comes here is the relation with the work of Agostini, Mazzuri, and Lorentzian. So last year, Agostini, Mazzuri, Lorentzian proved the following. So regarding the mass, if the manifold is asymptotically Schwarzschild or Schwarzschild, and then they prove that this expression goes to this mass over C. And this expression on the left, if you compare it to the one that you see on the previous slide, let me give it a name. Let's call this AT, script AT. And let's call this script BT. I think I use this notation later in later slides. So let me introduce it now. And then this quantity is AT subtract BT. Okay, so that's the relation between these mass limit. So in particular, one sees that the previous mass formula shows that the difference of AT minus BT under this general asymptotics is 8 pi times M over C. And moreover, in their work, they have this very important monotonicity. So regarding this difference, AT minus BT, Agostini, Mazzuri, and Lorentzian, they prove that this quantity is actually monotone. All right. With this in mind, prompted by the mass formula that we just see, we found indeed there are other monotone quantities. Okay, here I list 3 monotone quantities. I'll talk about A in a second. First, let's look at it. Oops. First, let's look at this I and the first one, well, the monotonicity about A and B. Okay, so the result is these two expressions themselves are actually monotone in the setting of asymptotically flat manifold. So in the previous slide, what we see is this difference. This difference, AT minus BT, was shown to be monotone by Agostini, Mazzuri, Lorentzian.
Sorry, and did those 3 authors also need this topological condition on the boundary that you have?
That's right. I mean, the assumption needed is to guarantee the level set of the harmonic function, say, to be connected so that you have the Euler characteristic bound when you apply the Gauss-Bonnet theorem. Okay, so regarding this monotonicity, so now you see this part and that part shows if you break the previous difference expression into the difference of 2 quantities, indeed, in the setting of asymptotic flat manifold, each individual factor is actually monotone. And combine this with the mass formula, you know each one of them tends to the mass over the C, in this case is the capacity ratio up to a constant. So then immediately you can you obtain applications. But before I talk about the immediate inequality you obtain by combining the mass formula and these two monotonicity, and let me comment on the first monotonicity, part A. Part A does not, so part A is something local. I mentioned that the monotonicity of this notation 1 and 2 below regarding AT, BT are something that's pertinent to the setting of asymptotically flat three-manifold. Because in the proof, one use the asymptotic flatness near the end. And the monotonicity of part A, this one is local. So in other words, I mean, in the simplest case, if you consider a product, assuming U has no critical point, and assuming U is defined on a compact manifold with two boundary components, and then that monotonicity holds as well. And that's a feature that's also enjoyed by the previous monotonicity of Angustiani, Mazuri, or Renzo. So in other words, this monotonicity star, this is a local monotonicity. Right? It does not need asymptotic flatness. One can prove that. And the next one, the one that I show you, part A, it's also a local monotonicity. It does not need asymptotic flatness. But now if you apply this monotonicity of A in the setting of asymptotic flat three-manifold, then you get to the monotonicity of 1 and 2 of AT, BT. All right, now let's talk about the immediate consequence of these mass formula and monotonicity. So those inequalities given by A, and number 1, number 2, those three monotonicities, I mean, those three inequalities now are nearly immediate from the previous two slides. For me, this part A, this inequality A is actually very useful. So what's the feature about this A? A does not involve mass at all. It's only a statement about the harmonic function U, which is 0 on the boundary, which goes to 1 at infinity. Okay, I will show the application of this part A in the part we call the geometric inequality group 2. Okay. But at this moment, let me give comment of the next two inequalities. So basically, the claim is given by the next remark. So either 1 or 2 implies the positive mass theorem in 3 dimensions. I do not plan to give a detailed explanation why any one of them will imply PMT, because later in the talk, in group 2 of the geometric inequality, there will be another result which almost gives PMT in a line. So for that reason, I do not want to spend too much time showing why these two inequality, why either one of them imply PMT in 3 dimensions. But I will just mention a very brief idea. So to prove the 3-dimensional PMT, it suffices to assume the manifold is topologically R3. Okay, that argument again is not obvious, but it's known. And then you do not need to worry about all the topological assumption you impose. And then to show the mass is positive, so you take a point, then you look at a small geodesic ball. And then you consider the harmonic function U, which is 0 on this geodesic sphere, which goes to 1. And then you apply either 1 of 2. And then you need to estimate, okay? You need to estimate the corresponding quantity, which is something one can do. So, okay, that's my comment about seeing PMT from either inequality of these two. as I said later, we will have another inequality which does not involve U at all. So that's something we will talk about later. And for the moment, I do want to spend a little bit more time on another monotonicity, also found recently. So last year, Montino and Wang, they discovered the following. So on a more general class of manifold, usually called non-parabolic, they found if you consider the minimum positive Green function, which is assumed to go to decays to 0 at infinity, then some expression is monotone. Okay, it's given. And then you apply this to the asymptotically flat free manifold, then you can use this monotonicity and the behavior of the asymptotic flatness at infinity, you get a sign of this expression. Below. Okay, this is completely a direct consequence of Montino's and Wang's work when you apply their result to asymptotically flat free manifold. So you have a sign of this expression. And then you can combine this fact with our mass formula 2.1.
Excuse me.
Yes.
May I ask, this result by Monteno and Wang, under which assumption it holds? Asymptotically flat, scalar?
No. Their result is in a more general setting. So they consider the so-called non-parabolic. So it's consider a complete three-dimensional non-parabolic manifold, assuming the minimum positive Green function at a point decays to 0 at infinity, and assuming the topological assumption. So in their setting, they assume the first Betti number is 0. Again, for the purpose to control the Euler characteristic of the level set. And then they prove this inequality. They prove this monotonicity. Okay, now, yeah. Okay, now,
they also do assume non-negative scalar curvature in that setting as well.
Yes, thank you. Thank you very much. Non-negative scalar curvature is assumed everywhere in this talk. Thank you very much. Yes. Okay, one thing I want to say is, so by now you have seen lots of monotonicities appearing so far. So it's natural. It would be a natural question to wonder, how are these monotonicity related? Are they just, are they there independent or they are related? That's a very natural question. And in a current work with Sven Hirsch and Lunfei Tan, and we are giving an account. We will give a unified account of all these sort of monotonicities. Okay, so that's just a remark regarding these existing monotonicities. So for this remark, my point is, if you apply Montino Wang's work together with the mass formula that I showed you earlier, then you also see why PMT is true. All right. The next corollary, I think is interesting. Okay, so first of all, this corollary is a corollary of these two inequalities of these two. So these two inequalities, besides they imply the positive mass theorem in 3 dimensions, they gave sufficient condition that guarantees the positivity of the mass. Let me draw pictures to illustrate what this corollary basically says. Say you have an asymptotic flat manifold with boundary, assuming non-negative scalar curvature, assuming the topological assumption so that the previous result apply. And consider a region that separate the boundary from the infinity, which I call it omega. And say its boundary has two components. I call S1, S0, S1. The reason I label them as S0, S1 is because you can consider a harmonic function completely on omega, only on omega, so that it's 0 on S0, is 1 on S1. And then this result says, if mean curvature of your boundary downstairs is less than or equal to this quantity compute on omega, then the mass is positive. So basically, using terminology from capacity, so this quantity on the denominator, so this is the so-called relative capacity of S0 with respect to S1. And very recently, or maybe 1 or 2 years ago, Jeff Jarogui did some very interesting work on capacity and the relative capacity and use them to detect mass. So that's something related. So here, the first inequality says, if the mean curvature of the boundary is bounded above by this quantity, depending solely on omega, and also in the C0 sense, and then you get the positivity of mass. And in particular, you can write down a very rough upper bound. So here, L is the distance between S1 and S0. And omega is the volume of, VOL omega is the volume of omega. So if the mean curvature of the boundary downstairs is bounded above by that quantity computed upstairs, then the mass is positive. Okay, that's the first inequality. The second inequality even does not involve sigma. Okay. The second inequality, or the second sufficient condition says, if this harmonic function u omega, which is defined completely on omega alone, if its integral on the initial surface is less than or equal to 4 pi, then the mass is greater than 0. Okay, as I said, these are direct corollary of the two inequality I mentioned earlier. I think it's interesting to talk about the application or implication of such a result. However, as I said, I do want to get to part 4 and part 5 of this talk. So if you have questions, we can discuss this after the talk. Now I do want to get to, so let me check the time, 10:15. Okay, so next, we want to consider this question. All the previous inequalities I show you, their rigidity holds on Euclidean space minus a round ball. And it's natural to seek inequalities which will be sharp on spatial Schwarzschild space. So that's a goal. And with a goal in mind, here is a quite natural idea. It's given an asymptotic flat manifold. So you have this you have this metric G, you have this capacitary function U is harmonic, and you want to get further results about this pair. And what you observe is you take another harmonic function V. Say V is positive. And then you can consider the conformal deformation. And then you get this G bar, which is conformal to G via V. Why you do that? This relation is revealed by the relation from Schwarzschild to Euclidean space. And this relation was used by Hugh Bray to get his mass capacity inequality using positive mass theorem. So making use this observation, so G bar is again asymptotic flat with non-negative scalar curvature. And you can also cook up a corresponding harmonic function U bar, which is V inverse times U. So the couple G bar U bar to this couple, you can apply all the results in group 1. the group 1 inequality. You apply it to this triple, and that gives you information of U and V. And then here you want to view V as a parameter. And then you may ask, for what choice of V, you may get some result which can be stated for you. So that's the idea. Applying that idea to group 1 inequalities, one gets the following. First, part A. So what's this part A? So part A in this group 1 inequality is the inequality that does not involve mass, which I said, indeed, I like this inequality. If you apply the idea using conformal deformation together with this inequality A, we get the one that in 4.1. This inequality 4.1 has the following feature. So U is global. U is a harmonic function that goes to 1 at infinity, which is 0 and the boundary. Therefore, this quantity is global, even though it's computed on the boundary. So this is a global inequality, but this result says if the scalar curvature is non-negative, that global quantity is bounded from above by a local quantity. Okay, as an immediate application, one thing one can ask is if one want to introduce the capacity, you can here now you use Cauchy-Schwarz on the left-hand side. Once you apply Cauchy-Schwarz, you recover a result that Bray and I had back to 2008. That result is an inequality on the capacity to area radius ratio. And you get the exact same result. However, back then we are using inverse mean curvature flow. And here the comment is using harmonic function. You get that mass, that capacity to area radius ratio. Okay, so this is one consequence. And then we can move on to talk about what are other implications of the inequality in group 1. And here is one involving the mass to capacity ratio. So mass to capacity ratio is bounded by this difference on the right. Now here, it's natural to say, I do not want this, I want to use something local. But then we realize that this integral, even though it's local, it has a upper bound by the Wilmore functional suitably written, which was on the previous slide. So if one plug in that lower bound, that upper bound of this integral square on the surface by the Wilmore functional, you get the next inequality. This is the result that I showed you in the first initial slides that Bray and I had. There, we need to assume this extra assumption that the mean curvature square, the integral of the mean curvature square is less than or equal to 16 pi. But here, here as a corollary, we find that this inequality indeed holds in general, together with the rigidity case. So the right-hand side, this lower bound is local. The left-hand side involves mass at infinity and the capacity, which is the global quantity. As application, the three-dimensional positive mass theorem follows. Why is that? Now you see this inequality does even not involve the harmonic function. So again, you look at asymptotic flat manifold with the background manifold being R3, you take a point, and then you take a small geodesic sphere. Apply this result to the exterior of this small geodesic sphere. And we have complete knowledge about the mean curvature of that geodesic sphere. So let the geodesic sphere be, if you shrink the geodesic sphere, you see the mass is non-negative. I have about 5 minutes, I think. So now I want to move to the final part. Okay, the final part is it seems this inequality, theorem 4.3, indicates it could be worthy of studying asymptotic flat manifold with boundary satisfying this mass to capacity ratio upper bound. Why is that? Coming back to this theorem 4.3. This theorem says this mass to capacity ratio is greater than or equal to 1 minus this Willmore functional normalized. Well, on one hand, one may argue if this mass to capacity ratio is greater than 1, is bigger than 1, then this inequality doesn't tell you anything. That's correct. On the other hand, for me, I see this inequality from a view that it seems this inequality indicates those class of manifold satisfying the mass to capacity ratio bounded from above by 1 may be of special interest. And next, I'm going to give some argument to try to support that that expectation. First, here are the examples. What are the examples of asymptotic flat manifold satisfying this condition 5.1? Well, first, any exterior region in a spatial Schwarzschild manifold. Okay, so here this is a Schwarzschild manifold with constant mass outside the horizon. Take any surface enclosing the horizon. Then the exterior region satisfies this condition 5.1. The reason is because for Schwarzschild manifold, M equals C. The capacity of the boundary equals M. Now, if you step inside, the capacity increase, and therefore this condition is preserved. For this part, I'm speeding up because of time. So next, you find this class of examples, all static extensions. Static extension with a positive static potential satisfying this condition 5.1 in the context of Barnick mass. Okay, so that's another class of examples. And next, in general, given any asymptotic flat manifold with boundary, it may not satisfy this condition to start with. But if you consider this harmonic function, the level set, if you step inside, for a controlled amount, then the region outside the level set satisfies this condition 5.1. So this shows this class of manifold is plenty. Moreover, it includes some very special, very canonical, some object of tremendous interest, say like in the context of Barnick mass. And here are some general properties. If you have a asymptotic flat manifold with boundary where this condition holds, and if you step inside, if you consider a surface S enclosing the boundary, then this condition is kept, or is inheritable when you pass from the boundary to a surface enclosing it. Even though this is a simple property, this is something that the other important geometric condition, the boundary being outer minimizing, does not enjoy. If you assume the boundary of this manifold is outer minimizing in area, if you go inside, take another surface enclosing the boundary, that surface does not need to be outer minimizing. But this condition, the mass to capacity ratio, yes.
Excuse me, just to make sure, there's some to the -1 missing, right?
Minus 1.
To the minus, I mean, as an
Oh,
exponent.
yes, thank you, yes, let me write it, yes, oh, thank you. Because both mass and capacity, they have lengths, they have the unit of the length, therefore, yeah, it's a ratio. The ratio is unitless, yeah. All right, so this is a general comment. The following two properties are indeed non-trivial. So if you have a manifold satisfying this condition, 5.1, then there is no minimum surface enclosed the boundary. No minimum surface. Such consideration does not occur. This is a consequence of Bray's result. Because if you have such a configuration, Bray's show, the result I mentioned in the very beginning, Bray's result shows the mass is greater than or equal to the capacity of this purple surface. Then you see this condition is violated. Again, this is something that's kind of desirable in the context of Barnick mass. Because when you minimize mass, you do not want to have a minimum surface enclosing the boundary. And another consequence of Bray's result is this condition singles out Schwarzschild outside horizon among all asymptotically flat manifold with minimum surface boundary. If you look at all asymptotic flat free manifold with minimum surface boundary, and if you impose that condition, you get Schwarzschild. Again, this is the consequence. This is the rigidity part of Bray's mass to capacity inequality. Having said that, the previous two slides are some general observation regarding that condition. In relation to group 1 inequality, here is something one can prove. Under the same assumption of the inequality that we mentioned earlier, if you impose this extra assumption, the mass to capacity ratio assumption, then you get more. Why you get more? If you expand this right hand out, you get 2 minus 3 MC inverse, and then plus a quadratic term of this quantity involved mass and capacity. If you ignore the quadratic term, this is inequality, the second inequality in theorem 3.1. But here, under this assumption, under the ratio assumption, you gain this quadratic term. There are consequences of this inequality, but I will skip them. Next, if you consider the class of all such extensions satisfying this mass to capacity ratio bound by 1, automatically the mass is bounded from above by a quantity that's determined by the boundary data. The reason is this assumption basically says M is less than the capacity. On the other hand, our previous result shows the capacity over the capacity to area radius ratio is bounded by the Willmore functional or normalized. So you get this result. The mass over of such extensions is automatically bounded from above. Next, the following quantity is, I found this is an interesting consequence, because this says under this mass to capacity ratio bound, then that global quantity has a lower bound. So what's U? U is a harmonic function. U is a harmonic function, which is 0 on the boundary, which goes to 1 at infinity. So U is harmonic. Now, if you assume this manifold satisfying this M over C less than 1 condition, then on the boundary, this integral cannot be small. It's bounded from below by pi. Heuristically, to me, it suggests that you should not expect such long cylindrical N. Okay, so to finish, it seems that it could be worth of considering a problem of, say, minimizing mass subject to this constraint in the context of Barnick mass. I noticed that Jeff in the afternoon will give a talk titled Minimizing Mass, Maximizing Capacity. And it seems that this, the condition that we see here is quite consistent with what Jeff is going to talk. So I will stop here. Thank you.